Okay. If you have attended my keynote presentation, this one would be a lot easy to comprehend, since this is kind of like subsurface geology, technical toward geologist, explorationist. So hopefully that would be useful to you. Let me get a pointer here, if you don't mind. Where is my pointer? Here is my laser. Okay. So what I'm talking about, finding oil and gas is not that easy, and it's very challenging. And drilling is the key or the backbone of finding oil and gas to drive a car, to fly, to get some stuff from oil production. Anyway, let's see what is that geomechanics are related to drilling. If we do not understand that geomechanics of the subsurface of the earth, how the earth moves, how the earth has a stress in it and strain, if we don't understand that, we will not be successfully to reach an oil trap and get you that oil and gas you need to your consumption, your domestic consumption. So it's very simple. I'm going to go through it quick. I have 6 segments here. Probably every segment is about 2 or 3 slides, and you will digest it easy. I went through that in the first presentation. It is a subsurface. In the subsurface, in the earth, there are 3 stresses: the principal, or the main one, and the minimum one. Those 2 guys control most of the drilling operation. The intermediate is okay, but it has another function, is minimal. In the past, 1948, this guy, he is from Hungarian, he came up with this model. There's 3 models. He said, okay, if I have a cylinder full of water and I have that spring sitting in the cylinder, and I push a stress on that cylinder without pushing any stress, that water is going to go out of the valve. And we call it hydrostatic. In the engineering and the geology world, it is hydrostatic. Then he locked this valve partially, just shut it off partially, and increase that pressure a little bit, so that start dripping, just leave it little dripping, and start moving that plate on the top gently down. He called it stage number 2. And there are lambda here. I don't want to bother you with the term, but now he came to a point that he shut the valve completely and increased the stress on that top plate. And he said, this is the stage where that overpressure build up. The pressure is, you see that pressure gauge right here. So in this case here on this stage, the fluid and the spring carrying that stress. And he came up with the idea, they call it the effective stress. The same like effective porosity, effective permeability, call it effective stress, which is the main stress here on the cylinder on the top minus the pore pressure. And that's what that idea of pore pressure came to the birth of the pore pressure idea. Now, in 1975, Mr. Eaton came up with that horizontal effective stress and the transformation model. What he's going to do, he's going to use the petrophysical properties, delta T here, and produce a pore pressure model, how the pressure developed in the subsurface. Here is 2,000 feet, here is 18,000 feet. So if I take this and build up a little model, show you that equation Eaton came up with, here is the effective stress, and using delta T to express that effective stress and the pore pressure, and instead of the cylinder of Terzaghi, the previous slide we show you. So we'll take the delta T and we see the compaction here. See the delta T increase. I mean, the velocity increase with depth, delta T decrease, and that's what we call the compaction. The sediment compact from here to here, and at certain depth, what is the top of the geopressure is no more compaction. The fluid get trapped. The same thing like Terzaghi, cylinder number A, where the valve was closed and the fluid does not escape anymore. So we're going to take that delta T, the observed, or the measured delta T, and the normal delta T, as if that extrapolated trend of normal compaction trend goes to the same depth. So we have two values, delta T normal, delta T observed. We put them here on the plot, and we say this is the effective stress. This is the prediction in the shale. We cannot use that model, Eaton model, in the sand. I've been preaching that 100 times. You cannot use the effective stress and Eaton equation in the sand. In the sand, or the reservoir is measured. You cannot predict it. This apply only in the low permeable formations, because we'll take this envelope here, that triangle, we're going to move it here. Okay? And then between the base of the shale, the top of the shale, this is going to be sand, is linear. Pore pressure is not just a zigzag line. No. It's a shale, sand, shale, sand. If you see a jagged edge pressure profile, this is somebody just take the last file and dump it on a software, and it give you that profile. Anyway, and it give us the privilege of exponent. We can change the exponent, and we come up with different prediction or different model. Here, what I came up with the last year. No, that's in 2015. I'm sorry. I'm mixed up between 2015 and 2025. I came up with, because I saw a lot of confusion here between where the effective stress is going to apply, here, there. So what I came up, this paper is being published in the OTC, AAPG, all over, was 4 zones. We have to divide the subsurface to 4 zones. Zone A, hydrostatic. Zone B is hydrodynamic, where the fluid leaving the system. So that's not a hydrostatic. This is hydrodynamic, means the fluid is moving. There is a flow. And here is the equation for the flow, for the pore pressure in that section. And then Eaton apply to zone C and zone D. So if you get the chance, read that paper. I think that's the OTC paper. Now, this is the conventional way. We have the hydrostatic, we have the principal stress, have the pore pressure in 2 segments, shale segment and sand segment. Do not or we do not predict this, the pool pressure in the sand. I just saw one yesterday, a paper, and they predicted this, that the pressure in the sand, it just is not. I've been saying that for a long time, since the 2001. Anyway, here's the frag pressure, here's the pool pressure, and in between the mud weight. This is the drilling tolerance window, but within the window itself, there is limitation, safety limitation. Here is the trip margin, and here is the kick tolerance. This is engineering terms, and it has another subject or another subject to go through it. Anyway, the geomechanical, okay, that's the segment number 2. I promised 6 segments, quick. The geomechanics setting. This is a copy of from M. Yasser, okay, I'll link them, and they will call it the normal fault, the strike slip fault, thrust fault. I mean, geomechanic has nothing to do, I mean, the fault is the result of the geomechanic. So I call it extensional, which is the basin extent. Compressional means that the basin shrink because it's uplift here, shrink. This is increase, and this is the slide slip is a shear system. Here it is. That's extensional. The basin open up, relax. Here is compression. So if we, in the conventional way, we consider the principal stress is vertical or the weight of the sediments, can we use that principal stress here as the weight of the sediments? Is no, because this is a compressional right here. That you get another power or another stress from sideway overcome the weight of the sediments. And I did apply this. This is another paper. I got it in 2024. That's last year in the interpretation, the APG SEG. I applied this to the thrust fault system. Yeah, stress sideway. It's not the overburden. And I review what I have done in the past. This is 24 years ago. I have this plot made by the drill work from the KSI. I did work for KSI for about 3 years. And here is the overburden. Here's the leak of test. And you notice here, the leak of test is higher than the overburden. So something fishy is going on here. So also, this is 24 years ago. This is 10 years ago. Fleming, he got the same thing, fell in the same trap I did 20 years ago. He used the overburden as the principal stress right here. Also, Zhang, that's about 8 years ago, did the same thing. Used the overburden as the principal stress. However, in that segment number 4, because the salt has unique petrophysical property, density, and we talk about this on the 40 minutes keynote talk, that if we introduce the salt here in that core, that above the salt is going to be the stress would be higher than below the salt, and this is on the flank of that salt layer. So here is the density, and because the salt is very flexible, when you bury it deep and put pressure on it, the weight of the sediments is going to move up. So what we have seen here, this is simulation of the real thing. This is the real thing. The salt coming sideways from up depth. And here is the stress model. This is principal stress S1, and this is S3. So the weight of the sediments become the minimum stress instead of the principal stress. And this is also published in 2024. See how that conventional pressure plot has completely changed. Above the salt, the principal stress higher than the overburden. So the frac pressure follows suit and the mud weight follows suit. In the salt, there are no change in the pore pressure whatsoever. Since the salt is clean, it doesn't have fluid, it doesn't have permeability. Any formation does not have fluid, it does not have pore pressure. Yeah, you have to have fluid. You cannot go to outcrop and say we're going to find what's the pore pressure in the outcrop. It has to be as fluid, which is mainly water. So, based on that, there are 2 wells has been drilled on that trend, that the flexure, the overthrust belt or the toe brand, and one of them a jack. Here is the overburden, which was a mistake to put the overburden here, but that's okay. It does not interfere in the calculation at all. And here is the frac pressure. Here is the casing points. Here is the mud weight. And the mud weight increased 3 pounds, jump from this point, enter the salt, before entering the salt, keep going, increase, 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 and then the frac pressure hit the mud weight, and the well lost circulation 100%. So what happened here? Why that I said in the model, the salt doesn't have fluid, it doesn't have permeability, so the pore pressure is supposed not to change. But if you have embedded sediments in the salt, and every time the drill bit hit that sediments embedded in the salt, it hits some pressure, and the tool pusher cannot respond to this, so increase the mud weight. And we set casing in the salt. You're not supposed to set casing in the salt if it's clean salt. And completely lost circulation at the bottom of the salt because the frac pressure and the mud weight, they overlap. Sidetrack and bypass about 3-4 times to save the borehole. Now, in the case, if I have a clean salt, that's another well, it's St. Molly. If the casing there and have a clean salt, the mud weight goes straight, no problem, penetrate the sediments below the salt, and go to the objectives. Here is your overburden, and here is the frac pressure. So obvious, in a clean salt, this well, it didn't take long to drill. It's about a month and a half. The previous well with the troubles here, it took about 3 months to drill. And imagine in deep water how much that drill ship cost. Here in the clean salt, no problem, no casing in the salt, no kicks, no loss of circulation, which was good. I did this long time ago when I used KSI software, and I recognized the leak-off test above the overburden. So this is the corrected principal stress instead of the overburden. This is the new numerical model in the salt thrust belt. if you want to predict pore pressure in the overthrust belt, which is Jack, St. Molly, Neptune, all these trend, that's the model you can use. Go read my article here and the interpretation. You're going to find out how did I make it. Also, you can predict the S1, which is the salt stress from that model, from building the model. You calculate the salt creep or the salt stress. Also, calibrating the pore pressure with the measured pore pressure. Here is an example of how we do it. Here is the predicted pore pressure, the solid line. Here is the measured pore pressure. And a lot of interpreters think that that line is supposed to line up with this measurement because we calibrate the predicted pore pressure. Look, you end up with two things. Here's okay, but down here is wrong. So your predicted pore pressure is way higher than the actual pore pressure, the measured pore pressure. So the best way to do it is to separate the predicted pore pressure in the shale from the measured pore pressure in the shale, in the sand, and make the calibration with different ideas from the mud log, from the gas kicks. Here is another pitfall. You take your RFTs or the measured pore pressure and the predicted pore pressure and try to match them to calibrate your model. That's a big problem because you end up with your predicted pore pressure is about 1,000 psi higher than the mud weight, which is this is not feasible. The good way to do it is like this. There are a lot of tools to calibrate with pore pressure, not by the RFTs and MDTs. There are a lot of items you can use. Also, why we drill a prospect? To find hydrocarbon. But most of the models do not encounter hydrocarbon in it. So, especially in the deep water, here we have 10, 1, 2, 4, 8 casing point, and here you have a pay zone. Pay zone means you get a hydrocarbon here. It is your frac pressure. That hydrocarbon led to make the drilling tolerance window shorter, smaller. Sorry, shorter and smaller. That subject to make your mud weight not capable to hold the pressure. And this is exactly what happened. This is this well is about 3 miles south of the Deepwater Horizon prospect. And whoever did it, nobody looked at it. So here is the Deepwater Horizon. What happened to it? Nobody knows. Everybody just say with this, that was wrong, Is the geology wrong? If the model, the pre-drilling model was adequate, they'd have used the salt buoyancy effect. Have they cleaned they add the hydrocarbon column to the model? Have they cut corner? They clean the gas in the mud several times? They have to clean the gas. You got gas in the borehole, you have to circulate, and then you have to clean the gas from the mud. Cementing, how the cementing job was good or not, the test, the pressure test, probably the fatigue. But that was led to a disaster. So the geomechanic setting is very important, and how to use it and how we use it is crucial for drilling for oil and gas. Here is a summary. You're going to read it because I'm running pretty close to my end time. You can read it from the recording. It is the geological building block is the foundation for the geomechanic? Yes. Predicted poor pressure usually in the shale, not in the sand? Yes. Principal stress is not equal to the OB all the time. In the extensional system, it is equal to the OB, not in the compressional system. Effective stress should be modified around salt basins and overthrust. I want to thank the GOP staff for giving me that chance to present this work. And if you have any question, shoot me that question on the chat box or talk to me, either one. Thank you very much.